Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
To the eye, optical glass appears empty. It has no moving parts or visible circuitry. Yet inside an advanced laser system, centimeters of glass determine whether a beam remains ordered. If flawed, the beam collapses into heat, scatter, and get distorted. Laser glass must satisfy a more severe requirement. The light must pass through without discovering that the glass is there. A microscopic bubble can redirect part of the beam. A trace metallic impurity can absorb energy. A variation in index too small to see can reshape the wavefront over the entire aperture. In high homogeneity grades, this variation is controlled to approximately 1 part per million. A laser is not simply bright light. Its photons are organized: phase, direction, and polarization. Maintaining phase and direction is the ultimate goal of high-grade optical engineering. This allows the beam to focus into a spot or deliver enormous energy in a short pulse. Order is everything. The first problem is refractive index, the degree to which the material bends light. A lens depends on this property to function, but if that index changes randomly, different parts of the beam experience different paths. The second problem is dispersion, time-separated wavelengths. The third problem is absorption. Even a minute absorbed fractions become heat, changing density and refractive index. Heat turns the optic into an unintended lens, thermal lensing. High fields concentrate energy at scratches. Optical glass manufacturing is not the production of transparency. It is the systematic removal of every mechanism by which glass interferes with light. The phrase laser glass hides two fundamentally different jobs. Most glass in a laser system is passive. It transmits or redirects the beam. Passive optics transmit or redirect the beam. Fused silica is selected for low absorption, but some glass is active. In these, rare earth ions are distributed to host energy. Neodymium ions are spread throughout, capturing and holding photon energy. These ions release energy into a passing beam through stimulated emission, amplifying the laser. The behavior of glass is encoded in its composition. Silica forms a highly connected network, but pure silica is extremely demanding to build. Multi-component glasses add oxides to adjust refractive index and durability. The designer must locate a narrow region where performance, manufacturability, and stability. The batch room establishes the chemical limits of the optic. Silica and specialty additives are weighed. Moisture can alter chemistry, while cross-contamination introduces absorbing species. A contaminant invisible to the eye can cause localized failure. For active glass, the dopant must be uniform. A gradient becomes a gain gradient, corrupting the beam's spatial profile. The batch room establishes the chemical limits of the optic. High-purity silica and specialty additives are weighed to a controlled formula. As ingredients react, they release gases. Bubbles must rise and exit the melt. Homogenization uses controlled mixing to reduce refractive index gradients called striae. Samples reveal chemical drift. The highest homogeneity material comes from periods of constant values. Synthetic fused silica is produced from purified chemical precursors in flame hydrolysis. By beginning with purified vapor, manufacturers suppress metallic contaminants. Once the melt is acceptable, it is poured into blocks or large molds. The liquid glass takes its geometric form during this phase. A large casting takes time to fill, and the glass preserves a pore. Convection near walls makes edges less uniform. The central region is selected for homogeneity. Glass is a solid that remembers its cooling. Above transformation, its network can rearrange. Uneven cooling creates mechanical stress. By refringence, different polarization directions experience different refractive indices. Fine annealing reheats the blank and cools it exactly. This delay is unavoidable for uniformity. The blank is transparent, but not yet an optic. It is inspected for bubbles. Diamond tools cut the blank. CNC generation creates geometry. Success removes the damaged layer. Polishing replaces frosting with clarity. Interferometers measure surface errors for deterministic correction. Measurement continuously rewrites the process. The surface must be smooth and chemically okay. Even perfect glass has an imperfect boundary. Light crossing from air to glass is not exception. Thin film coatings control this boundary. Alternating layers create a transmitting surface, but coatings introduce failure modes. A nanoscale defect can seed a damage site. Coatings determine the lifetime of the optic. Quality cannot be established by sight. A piezo-interferometer maps optical path differences. Wavefront error equals thickness times index variation. 1 part per million variation distorts the wavefront. Metrology closes the loop back to melting and annealing. Each process is corrected. The National Ignition Facility uses 192 beams and 3,000 glass slabs. Flash lamps deliver intense white light, and neodymium ions absorb this energy, entering high-energy excited states. An infrared pulse at 1053 nanometers passing through triggered stimulated emission, amplifying the beam. Meter-scale elements require a continuous pour process. A stable stream for the world's largest laser. Perfect glass does not exist. Every melt contains variation. Every casting records its flow. Every cooling cycle leaves a structural history. High-grade manufacturing makes imperfections smaller than the system can detect. Invisibility is an act of engineering. To reach this level of perfection, we return to the batch. The first optical component. Metallic ions become heat sources under high energy. Elimination is absolute for laser stability. Thermal management inside the melt is a game of millimeters. Convection must be balanced. Continuous tank melting is about time. Stability over weeks creates the required homogeneity. The structural memory of glass is persistent. Any gradient during cooling remains locked as internal stress. Annealing allows molecular chains to reach uniform density. This protects the refractive index. Network. Metrology is the final arbiter. Piezo fringes tell a story the eye cannot see. 1 part per million uniformity is achieved, a material that light truly cannot notice. The journey of laser glass is one of systematic elimination of every possible error, a material designed to vanish so light can perform its most powerful scientific work. Glassmaking is ancient, but optical engineering is a recent chapter. The transition from art to exact science happened inside the industrial furnace. This transition defines the modern manufacturing era. By changing ions, we create glass for unique laser applications across every industry. From fiber optic cables bridging continents, to the lasers performing life-saving surgery, the purity of glass is the common thread. Deterministic polishing allows us to reach meter-scale optics once thought impossible in science. As we push toward petawatt lasers, the requirements for glass will only increase. Precision is not just a goal, it's the starting point. Every nanometer matters. Light travels through these components with no obstacles, no scatter, no distortion, path. The energy is focused, the phase is preserved. The laser performs exactly as designed, thanks to the engineering of the invisible material. This is the legacy of optical glass manufacturing, a material designed for light. Additional technical sequences following the main documentary start now. Calibrating precision sensors for the next phase of manufacturing observation. Observing the structural history being written into the glass at a molecular level. Resetting the piezo-interferometer for a second inspection pass of the slab. Maintaining absolute sterile conditions for the high-purity batchroom operations. The liquid glass finds its form as it slowly cools toward the transformation range, ensuring the thermal gradient remains zero during the critical structural freeze. Recycling the polishing agents to ensure zero waste in our precision foundry. Achieving the perfect vacuum for ion beam sputtering of the dielectric layers. The material is now ready to disappear into the highest energy laser on Earth, checking the beam for zero distortion after passing through the new glass slab. Standing by for the next batch of raw materials to enter the purity chamber. Mapping the clean optical path through a series of 50 high-grade lenses. Measuring the energy gain after stimulated emission in the active glass amplifier. Preparing the next set of flash lamps for high-energy pumping of the NIF slabs. Zero contamination achieved. The foundry remains a temple of precision, simulating the phonon interactions within the phosphate network at high energy. Scrolling through the homogeneity maps of the last 100 production boules, dissipating the thermal load after a successful high-power laser firing cycle. Precision manufacturing in silence. The material light cannot notice is built here. Simple Gyan engineering. Industry, knowledge, and skill.